If you're like most students, you probably have a difficult time working ratio proportion problems. I'm going to show you a method that should help you considerably. You won't need to use this method forever, only until you feel comfortable in solving this type of problem. Most students don't have problems solving ratio proportions once these problems are set up correctly. But if you guess where the numbers go, you only have one chance in 3 that you will get the right answer. Let me show you why that is true. Once you have any ratio proportion problem set up, it should always have a form similar to this. X divided by A is equal to B divided by C, where A, B, and C are given numbers and X is the unknown value. For example, X divided by 3 is equal to 36 divided by 8. You don't have to call your unknown X, but X is used very often and will be used for the unknown in the rest of this discussion. It is important to recognize that if the number that is diagonally across from X is not the correct number, then you will get the wrong answer. Since there are 3 numbers that you must have to solve a ratio proportion problem, you only have a 1 chance in 3 of getting the answer right if you guess. When anyone first learns how to solve a ratio proportion problem, he or she must understand all of the details. As that same person practices more and more, there is a tendency to go into autopilot mode, solving the equation without a lot of thought. That is great while you are becoming technically proficient in solving such problems, but it is terrible if you are a teacher because you have forgotten what you need to know to teach students what they need to know. So let's go back to the basics. I like to use tables to gather and organize information in a problem. At first, I drew boxes, but I realized that a tic-tac-toe board worked better. Start by drawing a tic-tac-toe board and putting an X in the middle square, like this. A ratio looks like a fraction, but it is really more complex than just a fraction. It is a comparison of 2 things. For example, suppose a recipe for an all-natural beverage requires 4 oranges and 3 apples. The ratio of oranges to apples is 4/3. By the way, this is the only time that I know of when someone can legitimately compare apples to oranges. In a ratio proportion problem, you must be given 2 ratios, although they may be disguised in the wording of the problem. So let's see how to decode the problem. We will first see how to do this in general, and then work through several examples. The 2 ratios will involve 2 objects and 2 characteristics of those objects. For one object, both characteristics will be given. For the other object, one characteristic will be given, and one will need to be found. Example number 1. A large scalene triangle and a small triangle are similar. The shortest sides of the triangles are 3 inches and 6 inches respectively. The length of the longest side of the larger triangle is 10 inches. What is the length of the longest side of the smaller triangle? You should remember that scalene triangles are triangles that, in general, have 3 sides, each having 3 different lengths, and also 3 internal angles, each having 3 different measurements. That information is not essential to solving this problem, but it will help you in the long run to know what the definition of a scalene triangle is. Many ratio proportion problems involve comparisons of large and small things. In this case, the things being compared are triangles, one big and one small. Now versus later is also a common comparison found in ratio proportion problems. With those general comments having been made, let us start setting up this problem. First, ask yourself what 2 things are being compared. In this case, it is 2 triangles. Second, ask yourself what 2 characteristics are associated with these things. In this case, it is the length of the longest side and the length of the shortest side of each triangle. Next, ask yourself which of these 2 things has an unknown characteristic. In this case, we are asked to find the length of the longest side of the smaller triangle. By the way, the unknown is almost always specified in the last sentence or question of any problem, ratio proportion or otherwise. So that's where you should look so that you know what the problem wants you to determine. Next, write the names of the things being compared at the top of the second and third columns of your tic-tac-toe board. The second column name should be the name of the object that has an unknown value associated with it, And the third column should be the name of the object for which you were given values for both characteristics. Your tic-tac-toe board should now look like this. In the second row of the first column, write in the name of the characteristic that has an unknown value associated with the item listed at the top of column 2. This leads to the following. In the third row of the first column, write in the name of the characteristic that has 2 values given in the problem for the item listed at the top of column 3. This leads to the following. At this point, use the information in the problem to fill in the blanks. Note that the first box in the first column is not used. If you want to put a problem number or other information there, such as your name, you are welcome to do so, or you can simply leave it blank. On your screen, you will note that we wrote example 1 in the upper left-hand corner of the box. Filling in the numbers in the blanks leads to the following. You can either erase the other information and put an equal sign between the 2 columns, or simply copy this information in equation form. Note the lower 4 squares in the box on the right-hand side. Your equation form reads like this. X over 3 inches is equal to 10 inches divided by 6 inches for this particular problem. Note that the measurement units, in this case, inches, cancel out on the right-hand side of the equation. Then we have x divided by 3 inches is equal to 10 over 6. The measurement units must cancel out on the left-hand side of the equation as well. For this case, the final answer must be in inches. Multiply both sides of the denominator, that is the bottom part of the fraction or ratio on the left-hand side, 3 inches, and then divide by 6 to get the final answer. X is equal to 10 times 3 inches divided by 6. And that simplifies to x equals 5 inches. It is always a good idea to check this out by plugging our final answer back into the equation we had originally. 5 inches divided by 3 inches is equal to 10 inches divided by 6 inches. Simplifying, 5 over 3 is equal to 10 over 6, and 10 over 6 is equal to 2 times 5 divided by 2 times 3, which is equal to 5 divided by 3 because the 2's cancel. Thus, we have found our final answer and verified it. Example 2. A tree casts a shadow of 20 feet at the same time that a yardstick casts a 2-foot shadow. How tall is the tree? This is a classic problem, and one that shows how to find the height of an object without climbing it. First, draw a tic-tac-toe board with an X in the center, just as we did in the previous example. Next, ask yourself what 2 objects are being compared. The answer is a tree and a yardstick. In the last line of the problem, we are asked to find out how tall the tree is. Therefore, tree goes at the top of the second column, and yardstick goes at the top of the third column. The characteristics being compared are the height of the objects and the lengths of their shadows. Thus, we fill in the box as follows. In this example, we need each column to be in the same units. A yardstick is 3 feet long, by definition. Now we can fill in the blanks. The lower right-hand corner of the tic-tac-toe board has the information for our equation. And here is our equation. X divided by 20 feet is equal to 3 feet divided by 2 feet. The feet on the right-hand side cancel out. We multiply both sides by the denominator, that is the bottom portion of the ratio or fraction, on the left-hand side, and then we get x is equal to 3 times 20 feet divided by 2, which can be quickly simplified to 30 feet, and that is our final answer. Of course, we need to plug our answer back into the original equation to check it. 30 feet divided by 20 feet is equal to 3 feet divided by 2 feet, and this simplifies to 1.5 equals 1.5, showing that our answer is correct. Example number 3. The distance on a Texas map from Dallas to Austin is 4 inches. If the map scale is 1 inch equals 50 miles, how far is it from Dallas to Austin? The 2 things being compared are the real world and a map. The 2 characteristics are actual distances and the reference or scale distance. The unknown is the distance in the real world from Dallas to Austin. This is how the tic-tac-toe board should be filled out. Example 5. A photograph is 3 inches by 5 inches. The photograph is enlarged so that the long side is 8 inches. How wide will the photograph be? What objects are being compared? A photograph and its enlargement. What characteristics are being compared? The widths and lengths of the photo and its enlargement. What is the unknown? The width of the enlarged photo. We fill in our tic-tac-toe board as you see on the screen, and we are ready to solve. The arithmetic afterwards is straightforward. One multiplication and one division, so we won't go into that. That part you should easily be able to handle. Students seldom make mistakes once the problem is set up properly. It is helpful to remember that in general the length is always longer than the width. So if a problem does not tell you otherwise, the larger of the two numbers is the length. Example 6. A certain cake recipe requires 3 eggs and 4 cups of milk per cake. If you have 9 eggs, how many cups of milk do you need to cook the maximum number of cakes with the 9 eggs? What objects are being compared? A cake made with 3 eggs and a cake made with 9 eggs. What characteristics are being compared? The number of eggs required and the number of cups of milk required in each cake. What is the unknown? The number of cups of milk required to make a cake with 9 eggs. Now, on your screen, you should see how this problem should be set up in tic-tac-toe board format. In the lower right-hand corner, again, we have our equation. We write it as x divided by 9 eggs is equal to 4 cups divided by 3 eggs. The measuring unit of eggs, which occurs in both the numerator and the denominator, cancels out. At first we have x equals 9 eggs times 4 cups divided by 3 eggs once we multiply both sides by 9 eggs. The eggs cancel out and we are left with x is equal to 9 times 4 cups divided by 3. And multiplying, we have x equal 36 cups divided by 3, which simplifies to x equal 12 cups of milk. Almost all measurement conversion problems can be solved as ratio proportion problems. Here is an example. Example number 7. How many feet are there in 10 yards? You may remember that there are 3 feet in a yard. Or you may look at a conversion chart and see that 1 yard equals 3 feet. What are the two things that are being compared? A reference measurement and the requested conversion measurement. The unknown is associated with the requested conversion measurement. The characteristics are the scale ratio and the actual ratio. On your screen, you see how this problem should be set up in tic-tac-toe format. Alternately, we could also set up the problem like this. You always have your choice as to whether to use rows or columns for the characteristics compared. Although, in my experience, it seems to work better if the items name the columns and the characteristics name the rows. But either way will work fine. Note that, in this case, we are calling the compared things the scale ratio and the actual ratio. The characteristics being compared are the reference measurement and the desired conversion measurement. But no matter which of these two ways we set the problem up, our solution process eventually leads to the following equation. X is equal to 10 yards times 3 feet divided by 1 yard. The measurement unit of yards cancels out since it is both in the numerator and the denominator, and when we simplify, we end up with x equals 10 times 3 feet is equal to 30 feet. Clearly we should go back and check this, but for now we'll overlook that and go on to our next step. Any kind of direct variation problem can be set up as a ratio proportion problem. Direct variation problems involve a formula like distance equals rate times time. Total cost equals unit price times quantity ordered. Power is equal to current times voltage. Voltage is equal to current times resistance, etc. To be more technical, these are all linear functions that have a y-intercept of 0. Let's look at 2 examples of this type of problem. Example 8. It is 240 miles from Dallas to Houston, Texas. If someone drives 60 miles per hour, how long will it take them to reach Houston? One way to set up the problem is as follows. On your screen, you note the items compared and the characteristics compared. Actual travel versus reference travel are the column titles. Time required versus distance covered are the row titles. X, as usual, is in the center. The reference travel is 1 hour. The reference distance covered is 60 miles. And finally, the actual distance covered is 240 miles. Clearly, all we need to do is set up X divided by 240 miles equals 1 hour divided by 60 miles, and we can use the same technique to simplify and arrive at our answer. Example 9. Apples are on sale, 4 for $1. How much will it cost to buy 10 apples? One way to set this up is as follows. Actual apple purchase and reference apple purchase are our column titles. Money required and apples purchased are our row titles. X, as usual, is in the center. You will note the actual purchase price is for 10 apples. The reference purchase price is $1, and that is for 4 apples. Recall that I said much earlier, very often comparisons are of big objects to small objects, or vice versa. Small triangles and big triangles, photographs and enlargements, blueprints and actual buildings. We can also compare now to later, as I indicated earlier as well. Here is an example of that. Example 10. 140 hot dogs were sold during the first 7 games of the Little League baseball season. If hot dog sales continue at this same rate, how many hot dogs will have been sold after 50 games? One way to set this up is as follows. We're looking for total hot dog sales after 50 games. That should be our second column title. Hot dog sales after 7 games, our reference amount, will be our column title for the third column. Our second row title is hot dogs sold. Our reference is 140 hot dogs sold. The third row is games played. That's 50 games in column 2 and 7 games in column 3. The second column is later, the third column is now. Be careful. Sometimes you may have to do some conversion first, which is another ratio proportion problem, as we showed earlier. For example, if a problem told you that 10,000 corny dogs were sold during the first week of the state fair, and the problem asked you to estimate how many would be sold during 21 days of the fair, you would need to either replace week by 7 days or the 21 days by 3 weeks. After you have become good at setting up ratio proportion problems, you can start using the tic-tac-toe system less and will still be able to set up the equation simply by reading the problems. The training wheels will be gone and you will be a master of ratio proportion problems. But while you are building up your skill, go slow and set up the problem the right way so that you will be sure you are getting the correct answer. Now you're on the road to becoming an expert at ratio proportion problems. Thank you for listening. Copyright 2009, James Davis.